In this example, we're going to find the plane z equals alpha x plus beta y that best fits these data here on the right. And we're also going to calculate the error vector. So now you're probably used to finding lines of best fits or curves of best fits. And this happens in 2 space. But when we're in 3 space, we're going to need to find a plane of best fit to fit these data. And now because all of the data points aren't going to perfectly fit on a plane that we find, there's going to be some error. And the error is the vertical distance from the point to the line of best fit. So that's the value that's going to make up our error vector. So now to find our plane of best fit, we're going to start out by writing each of our points in this form here. So basically we're going to sub in our x, y, and z coordinates, and we'll have an error component as well. So our first point, we have 10 as our z value, then x is 1, so that just leaves alpha, and y is 1, so we just have beta. And we also have our error term. Our next point, z is equal to 30, x is equal to 1, y is equal to 2. We have our error component. Our next point, z is equal to 20, x is equal to 2, y is equal to 1, and then our error component. And finally we have z is equal to 50, x is equal to 2, and y is equal to 2, and then our error component. This can also be written in vector matrix form. So we have our vector z on this side. Then we have matrix x, which is made up of the coefficients of our alphas and betas, or which is also the same as our coordinates x and y. So these are our coefficients of alpha, or our x coordinates. These are our coefficients of beta, or our y coordinates. Then we hit that by alpha beta. Now all we have left are error terms, so they go in their own vector. So this can also be written as vector z is equal to matrix x times our beta vector plus our error vector. And now the least squares solution will happen when our error vector is orthogonal to the columns of x. And when our error vector is orthogonal to the columns of x, then if we hit our transposed x matrix by our error vector, then we're going to get 0. So what we're going to do now is we're going to take this equation here and hit each term with our transposed x matrix. So we're going to end up with x transpose z equals x transpose x by our beta vector plus x transpose our error vector. And as I said earlier, our x transpose by our error vector is going to be equal to 0. So this term disappears from that equation. So now what we're going to do is we're going to calculate our x transpose z and our x transpose x times our beta vector. So to get our transpose matrix, what we do is we take the first column of our x matrix, and that becomes the first row of our transposed matrix. Then we take the next column, and that becomes the next row. And we're just going to hit that by our z. And on the other side we have our x transpose matrix again. Then we have our regular old x matrix. Then we have our alpha beta. So from this point we want to find our alpha beta, and what we're going to do is matrix multiplication on each side. So just as a reminder, to do matrix multiplication, you're taking the dot product of the first column with the first row. So the dot product would be 10 times 1 plus 30 times 1 plus 20 times 2 plus 50 times 2. Then you do the same for the second row, and that's going to give you 190. And so you do the same thing again, so the dot product of this by that gives you 10. Then the dot product of this column by the second row, that gives you 9. Then the dot product of this column by that row, that gives you 9 as well. Then the dot product of this column by this row, and that gives you 10. Then we have our alpha beta. Now what we want to do is we want to isolate our alpha beta here. So we're going to bring this matrix over to the other side by taking its inverse. Now just as a reminder to take the inverse, you have 1 over the determinant, which is 10 times 10, minus 9 times 9. And then we're going to swap the entries in this diagonal, which doesn't really matter in this case. And we're going to make the entries in the other diagonal negative. Oops. And we don't have that negative 1 there anymore, sorry. So if we calculate this matrix multiplication like we did earlier, then we're going to end up with 1 over 19, 90 to 80 is equal to our alpha beta. So now we have our alpha beta. So if we go back to this equation up here, we know this and this and this. So all that's left to find is our error vector. So let's write out that equation again, but we'll sub in all the things that we know. So there is our z, matrix x by beta vector plus our error vector. So our z vector, we have 10, 30, 20, 50, and again those are just the z coordinates from our points. Then we have our x matrix, which we found earlier. Then we have our alpha beta, which we know now, it's over here, so we're going to sub that in for our beta vector. Then we have our error vector. Now just to make this a bit easier, I'm going to multiply everything by 19 to get rid of this fraction here. So 19 is going to go in front of this one. And we're going to get rid of our fraction in front of that term. And then we get 19 in front of our error vector. Now I want to isolate this vector here so we can solve for our error vector. So I'm just going to bring over all of this stuff to the other side. Now if we calculate out this matrix multiplication here, we should end up with, so we have 90 times 1 plus 280 times 1. Then we do the same thing for the next row, 90 times 1 plus 280 times 2, and so on. You go down each row. And then we'll multiply 19 by each of these entries here, and then we'll subtract all these entries from these entries over here. So if you do those two steps, what you end up with is 1 over 19 on this side, and here is our error vector. So this tells us how far each of our points are from the line of from the plane of best fit, sorry. And this tells us the values that we should sub in to to this equation here to get our plane of best fit.